Welcome to Chapter 12. Chapter 12 deals with sequences and series, and so we'll start looking at 12.1, which is sequences. A lot of work in our calculus class will be dealt with sequences. If my memory serves me correctly, it won't be until you're in Calc 2 that you'll utilize sequences and series a lot, and then certainly a little bit more in Calc 3. But in Calc 2, it's a underlined um, kind of a topic for a lot of the work that goes on there. And so we want you to be familiar with it as it gets brought up. And so a sequence is a function whose domain is a set of positive integers, right? So we're only plugging in numbers that are the counting numbers, 1, 2, 3, 4, 5, 6. They're basically position holders. We use n to represent the domain of the function. To find the range of the function, you would substitute the values of n into the function and then list the outcome with a comma between the values. So the first term is found by substituting the first domain element, n equals 1, into the function that defines the sequence. The second term is found by substituting the second domain element, 2. So you're just going to be plugging in 1, 2, 3, 4 into a prescribed formula. And so there's several different things we do with sequences, but as we look here at this first example, they're going to look at a sequence who's being defined as take n, double it, and subtract 1, right? And so n equals 1, you're going to get 1 out. N equals 2, you're going to get 3 out. N equals 3, you get 5, 4, 7. Plugging in n equals 5, you get 9. Obviously, if we plugged in n equals 6, we get 11. And what we find is we're generating all the odd numbers through this sequence. I apologize. And they're separated by commas because there's no other domain elements in between. Or apologize, I said domain. There's no other range elements in between. We're plugging in the positive integers, right? Just the counting numbers, and we're getting out these specific terms. And so much of the work in chapter 12 is pretty nice because it's an introductory type of thing. So he's just kind of going over what happened. This is more what we do. We typically don't represent it in function notation. In fact, I don't really feel like I've ever seen that before. And one of the reasons, well, no, that's not true. I was going to say one of the reasons is we're skipping stuff. It's not a continuous function, but it is a function. We typically see the an though. An is equal to 2n minus 1. Same definition, right? 2n minus 1. And so you're getting out the same 1, 3, 5, 7, 9 when you look at that. So some of the homework's just going to have you list out the first few terms, first 5 terms in this case, and you're literally just plugging numbers in. They're defining here in example 1, an to be 3n minus 2. If it's a sequence, which these all are, you're going to be plugging in successive positive integers, 1, 2, 3, 4, 5, and get a1 is 1, a2 is 4, a3 is 7, a4 is 10, a5 is 13. Notice 3 is being added every time. It's no coincidence that there's a 3 there. So negative 4 and plus 1. If we go over here to example 2, and we plug in 1, 2, 3, 4, and 5, and look what we get. Negative 3, negative 7, negative 11, negative 15, negative 19. Just to help you for future sections, look what's happening every time we're dropping 4 to get to the next one. Well, here's that negative 4 right there. The one question is where do we start? Well, we can always figure that out by plugging in 1. But at some point we realize, hey, I can take advantage of that negative 4. Not all sequences are like that. We won't be able to do the same thing here because of the powers that are involved. So here we have in example 3 a sequence that's defined as 2n squared minus 1. When it's not rocket science, all we're going to do is plug in 1, then 2, then 3, then 4, then 5, right at the very end there. So this last one should be 5s. So as we plug in, you can just watch the math work out. You are not doing really any difficult type of arithmetic. All can be done without the use of a calculator. And so one thing that I haven't pointed out is the n general nth term is exactly the same as the n general nth definition. So this is just telling us, this original an is telling us, hey, this is what all the terms behave like. You want the 77th term? Go ahead and plug 77 in, right? It's that easy. There are some times where it's defined in what we call a piecewise manner. N if n is odd, n squared if n is even, and it kind of just bounces back and forth. So if you plugged in 1, since 1 is odd, it's going to stay as a 1. You plug in 2, since 2 is even, we're going to square it and get 4. 3 going to stay as 3. 4 is going to go to 16. 5 is going to stay at 5. 6 is going to go to 36. So forth and so on. Gets a little bit difficult in these piecewise ones to name the nth term because the nth term could be one of two things. It could be n or it could be n squared depending upon what n is. And so we won't see it that way. One thing that we want you to become aware of is how you can switch signs. Right here is how we're able to switch signs, taking -1 to a power. And notice that the power won't matter. It matters in the sense of who starts out to be negative. So for example, with the way example 6 is defined, when you plug 1 in, you get -1 to the first power, which is going to be -1. And so your overall result is going to be negative. So we get 5 minus 4, 1 times -1, -1. 5 times 2, 10, minus 4, 6, times -1 squared. Now it's going to be positive. So it's going to alternate between negative and positive because of that. If you wanted it to start out positive, all you would have to do is adjust that by 1. It could actually be one of two things. It could be n plus 1 like he has, but it also could be n minus 1. That would also allow it to start positive as opposed to starting negative. And you can see that we get the exact same results because the 5n minus 4 hasn't changed. But we get the opposite signs happening. So pretty cool, something to be aware of. So let's go finding what term a number in a sequence is. So example 1 says, here's the in general definition of the nth term, 7n minus 6. What term has the value of 50? an equals 50 for some value of n. Well, we know how to do that. We're going to set 7n minus 6 equal to 50. And we're just going to solve for n. That would tell us what the n is. And so if evidently 50 is the 8th term in the sequence. Here, we want to know, hey, n squared minus 2, what gives us 14? Well, that's going to be when n squared is equal to 16, or when n is equal to 8. Now notice, technically, it should be plus or minus 8. However, we know there's no negatives because n is a positive integer. It's a counting number. So just like when we use the Pythagorean theorem for a triangle, we don't even consider the negative because there can't be a negative distance in length. Here we're not considering the negative because we're just plugging in the positive integers. But we should always keep in mind that plus or minus should be considered, and then we naturally look at it. And so let's take a look. We got a different answer. Maybe I'm wrong in what I was doing. So n squared is equal to 16. I was wrong. Apologize for that. I'm not going to go back and recreate the video. I am going to show you that I'm human. The square root of 16 is 4, right? I divided by 2. Silly me. And so we end up having the correct identification of the 4th term. Now, sometimes they are defined in what we call recursive formulas. Now, he has some words written there, but a recursive formula says, hey, this is where we start, and this is how the very next one is achieved. So if you look at the first example, it's saying, hey, we're starting at 2, and if you want to know any particular term, take the previous term and add 6. And for n greater than 1. And the reason why they have to put n greater than 1 is we don't want you to apply that to 1 because there is no 0 term. So, but they'll always give you the first term, and they'll always tell you how the next term's achieved if you knew the previous one. And so recursive definitions will be used a lot. You'll use them in a process called mathematical induction. And so its principles lie even beyond sequences and why it's shared with you in books. So if we took a look at this, if the first term is 2, then the second term is going to be gotten by adding 6 to the first term. And so the second term is going to be, I don't know why he doesn't list it here. A1 we know is 2, so we get an 8 out of that. Now we're going to take 8 plus 6 and get 14. Now we're going to take 14 plus 6 and get 20. And then we're going to take 20 plus 6 and get 26, and so forth and so on. So you could just keep adding 6 to the last term. And so you can read through that narrative on your own. So a Fibonacci sequence is only defined recursively. So he's going to bring up that sometimes that's the best you can do, because it's very, very difficult to give an in general definition to something like this. In fact, probably impossible, since I've never seen one for the Fibonacci sequence. So A1 is equal to 1, A2 is equal to 1. That's very unique. And then if you want to know the nth term, you take the two previous terms and add them. So take a look. 1 and 1, and then take those previous two and add, you get 2. Take the previous two and add, you get 3. Take 2 and 3 and add them, you get 5. 3 and 5, 8. 5 and 8, 13. The only way to really describe that is through a recursive definition. Right? And so he's kind of showing you that, hey, 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. And we could just keep going. 5 and 8 is 13. And he does over and over, right? And you just get this nice Fibonacci sequence. And then he's talking about a spiral here. When you make squares with those widths, you get a nice spiral coming through. And so he's just going to give you some history here. Fibonacci's numbers are nature's numbering systems. They appear everywhere in nature, in leaf arrangements and plants. So just something that you don't need to know in order to be able to do the homework, but has you realize that a Fibonacci sequence wasn't just made up because it was actually observed in nature, and he's going to show you that right there. Let's take a look at other things that could happen. So find the first 5 terms of this sequence that's defined in recursive forms. There's going to start out with 4, and what we need to do is add 6 every time for n greater than or equal to 2. So that's another way to say don't do it for 1. So we're going to take that first term and add 6 to get 10, add 6 to that to get 16, add 6 to that to get 22, add 6 to that to get 28. And that's using the formula. And so here's the English, right? That's what I was just going over, is the English. If you understand what the math means, you just talk yourself through it. The more you can give English language to mathematical ideas, the better you'll do at both comprehending and also doing. And so that's a great way in English. So you're looking at this one. It's telling you what the first term, and actually this should be the second term, what the first term and second term are. And what it's telling you to do is to get any term, you need to add add the previous 2. So if we want to get the third term, well, no problem. We add the 7 and the 9 to get a 16. If we want to get the fourth term, we're going to add the 9 and the 16 to come up with 25. To get a fifth term, we're going to add the 25 that we just got to the 16 prior, right? And so you can start to see, we started out with these two, add them to get 16. 9 plus 16, 25. 16 plus 25, 41. 41 and 25, 66. And so forth and so on, right? The next one would be, 107 coming through there. So adding those previous terms. Famous sequence examples. Integers starting with 4, integers starting with -3. I'm not sure why these are wonderful examples here, but you have even integers, 2n, integers starting with 6, 2n plus 4 would do that, right? So what he's showing you is those things that come out. If you had a 2n minus 6, you get even integers starting with -4. Odd integers, 2n minus 1. Odd integers starting with 9, 2n plus 7, and so forth and so on. Powers of 2, obviously 2 to a power coming through. 1 more than a power of 2, 2n plus 1, 1 less, 2n plus 1, powers of 3, 2 more, right? Pretty self-explanatory. Triangular numbers. This happens sometimes where you take 2 numbers and multiply them together, n times n plus 1, to get you to the next, or to get you your n terms. So remember, this is the n, this isn't an times an plus 1. I hope I didn't misspeak there and confuse you. That is not what they're saying. They're saying take the n that you're plugging in, 1, and go one more integer up and multiply them. So 1 times 2 is 1. Oh, 1 times 2 is 2. Oh, apologize. I see what the ends are here at the bottom. So 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12, right? 4 times 5 is 20. So this is the fifth term. So we're going to take the number 5 times the number 6, and that is going to be our answer up there. A pattern based on factors. So 2n times 2n minus 1, right? We could do that. Alternating signs, we talked about that earlier, and negative 1 to the n would do that. And starting with the plus 1, you'd have to do an n plus 1, or technically an n minus 1 works as well. So I think in this, as you go through the homework exercise set, you're just going to get familiarity in this first part of 12.1 with just the understanding of how sequences are described, and see if you can come up with certain terms that are there. So give it a shot and let me know if there's problems as you're in the homework.